Good morning, students. Let us start the class. In the last class, I was showing you this particular exercise. A discrete ergodic Markov random process is represented as shown. I had told you what is meant by discrete means symbols will be emitted one after the other. You are already familiar with the microcontroller and microprocessor architectures, where any microcontroller or microprocessor will have a 8-bit data bus or a 16-bit data bus or a 32-bit data bus or even a 64-bit data bus. In future, it may become a 128-bit data bus as well. Only in such systems where microprocessor and microcontroller can have parallel information paths, means if a microprocessor system is having a 16-bit data bus, then all the 16 lines can emit symbols simultaneously. But it is not possible in the other wired or wireless communication as such, where data has to be transmitted serially. If at all we want to have a parallel data transmission, it requires an abundant resource of communication. So in general, even inside the microprocessor or microcontroller system, even if the data is processed parallelly, when the data comes out of the same system, there is a parallel to serial conversion. Again, when the microprocessor or microcontroller system receives data serially, there is a serial to parallel conversion inside. You are already familiar with this USB. USB is basically universal serial bus, which is nothing but only 4 lines in USB. One is supply and one is ground and one is data and one is clock. That's all, only 4 lines, out of which only a single data line. And in that single data line, data is transmitted with reference to the clock. And along with that, there is a supply voltage and ground. That's all. So it is basically a serial data transmission in which the emission of symbols is discrete. Either a 0 will go or a 1 will go, and 0 and 1s will go on one after the other. That is a discrete transmission. Ergodic, I have already told, the one which is time averaged is called ergodic information source. Markov, I have already told, it is a method of modeling a stochastic process. And random, I have already told, random is nothing but a stochastic process where events seem as if they are happening randomly, but those events have their own information content. That way, a discrete ergodic Markov random process is represented as follows, where the process is represented only in 2 states, state 1 and state 2. If the system comes back to state 1, then it is emitting symbol A. And if the system is coming back to state 2, it is emitting symbol B. Otherwise, it is emitting symbol C. That is how it is represented. You already know that the emission of symbols happen only during transition. That means when the system has a transition from one state to the other. So you can see here, A will have a probability of 3 by 4, B will have a probability of 3 by 4, whereas C will have a probability of 1 by 4, because C is emitted only during interstate transition, only during interstate transition. Otherwise, within state 1, A is emitted, within state 2, B is emitted. Now, as we assume that all the states have equal probability, P1 is half and P2 is half. That is because this process is having only 2 states. So now, it is asked here, find the source entropy H and the average information content per symbol in messages containing 1, 2 and 3 symbols. In the last class, I had discussed about the symbol capital G along with the symbol capital H. That capital H is the source entropy, whereas when the source emits symbols, maybe in a sequence of 1 or one sequence having 2 symbols or one sequence having 3 symbols. For example, A, B, C taken individually is one symbol each. Otherwise, it can be AA, AB, AC or BA, BB, BC. That is two symbols. Otherwise, it can be AAA, AAC. Same way, it can be BBC, BBB, or it can be BCA, or it can be ACB. There cannot be a sequence of ABC, because you know that only during transition from one state to other state, C is emitted. So there is no chance of ABC. There is no chance of AB also. There is no chance of BA also. So based on this particular state diagram, we can write the tree diagram, and based on the tree diagram, we can actually find out the information content per symbol in the messages containing 1, 2 or 3 symbols. Later on, we can compare all these G1, G2, G3. G1 means information content in a single symbol emission. G2 means 2 symbols emission. G3 means 3 symbols emission. And H is the source entropy. So we can find out all these. Finally, we can compare and we can see the theorem which we had discussed earlier is being satisfied. So let me proceed with the solution. Now the source has 2 states and the source emits 3 symbols A, B and C. Entropy of each state is computed based on the symbols being emitted, which is given by H1 equals 3 by 4 Lg of 4 by 3 plus 1 over 4 Lg of 4 by 1. That is the entropy of state 1, because there only A and C are emitted. That is 0.8113 bits per symbol. Similarly, H2 is the same. It is 1 by 4 Lg of 4 by 1, because in state 2 only C and B are emitted. So that is also 0.8113 bits per symbol. Therefore, the source entropy is now given as total entropy H equals P1 H1 plus P2 H2, where P1 is the probability of state 1 and H1 is the entropy of state 1. Similarly, P2 H2. So as P1 and P2 are half each, we get this total H is 0.8113 bits per symbol. This is now source entropy. Now we will have to write the tree diagram for finding out G1, G2, G3. So the tree diagram can be written as, there will be 2 tree diagrams now, one for each state. Let us write it for the first state. The first state is 1. Now it can go from state 1 to 1, again 1 to 1, again 1 to 1. Or it can go from state 1 to 1, 1 to 1, 1 to 2. Because we have to consider 3 symbol emission as well now. Similarly, it can go from state 1 to 1 to 1 to 2, again 2 to 1, 2 to 2. Same way 1 to 2, 2 to 1, 1 to 1, like that it goes on. Now you can see in each emission of symbols, let us say from state 1 it is going to state 1, A is emitted, again state 1, A is emitted, again state 1, A is emitted. Total it is A, 3 symbols emission. In the same fashion, we can write for AAC, ACC, ACB, CCA, CCC, CBC, CBB. This way. Now, during each transition, we know the probability of that particular symbol's emission. Now, that can be written on each path. State probability is half, then the probability of A is 3 by 4, again C is 1 by 4, B is 3 by 4, C is again 1 by 4. This way we can complete the tree diagram. Now, using the tree diagram, we can compute single symbol emission, 2 symbols emission, 3 symbols emission. So you can see here, it is now A, here it is AA, here it is AAA. Similarly, here it is A, here it is AA, then it is AC. That way, all these totally 8 sequences, their information content can be calculated based on this particular tree diagram. Similarly, there can be another tree diagram for state 2, but the computation will be same as such, because the probability of A and probability of B are same. So I will show you the other tree diagram for the other state. Now it is for state 2. For state 2, it is now CAA, CAC, CCC, CCB, BCA, BCC, BBC, BBB. Now, if you compare these two here, there are some common sequences. For example, this CCC is occurring from state 2's emission as well, and the CCC is occurring from state 1's emission as well. So, naturally, the sequence CCC is emitted twice because it can happen from both the states 1 and 2. So, all these common sequences which are emitted have to be considered while we compute the information content per sequence there. Please remember this. CCC I have shown you. Similarly, is there anything else? Let us see CCB. Is it there? CCB is not there. CBB, is it there? CBB is not there. Okay. BBB cannot be there in the upper diagram because we started from state A. There AAA is there. AAA cannot be there from the lower tree diagram. So that way, if we see whatever is starting from C, that is CCA, CCC, CBC, CBB. CCC is there, then CCA is not there. That means only CCC is common. Other things are not common in the other tree diagram. Okay, with this observation, let us proceed for the computation of information content per 1 symbol, 2 symbols and 3 symbols. From the tree diagram, we can compute the probabilities of the messages of length 1, 2 and 3. Now you can see again, in the upper tree diagram, there is A and C. In the lower tree diagram, there is C and B. That means C is occurring in both the tree diagrams. From state 1 also, some state 2 also, C is being emitted. So that has to be considered now, even for a single symbol sequence. So now, messages of length 1. P of A is half into 3/4 is 3 by 8. P of B is half into 3/4 is 3 by 8. P of C is half into 1 by 4 plus half into 1 by 4 equals 1 by 8 plus 1 by 8 equals 1 by 4. This is because C is occurring in both the tree diagrams, whereas A and B are occurring in only single tree diagram. That is why this is the messages of length 1. So the average information content per symbol, that is G1. Now G1 can be computed. Average information content per symbol in messages containing one symbol is, now G1, you remember that formula 1 over n and summation of all that. Please remember that formula Gn. Let me show you that again. See, Gn is 1 over n summation of capital P, P of Mi into Lg of 1 over capital P of Mi. This capital P stands for the joint probability. So, using this formula, we find out now G1. So, G1 is 1 over n. N here in this case is 1. So, that is the summation of 3 by 8 Lg of 8 by 3 plus 3 by 8 Lg of 8 by 3 plus 1 by 4 Lg of 4 by 1. That is the summation of all these capital P. This capital P is nothing but joint probability now, because that includes the state probability as well as the transition probability. So now G1 is 1.5614 bits per symbol. This is the information content per symbol when one symbol is transmitted per sequence. Similarly, let us compute messages of length 2. P of AA from the tree diagram. I will not go back to the tree diagram now. You can refer to it again later on. I have anyhow uploaded these notes in the Google class. You can all download it and you can go through the notes for your reference. P of AA is half into 3 by 4 into 3 by 4 because first state probability and then the transition probability and then the transition probability, it is same 3 by 4 only for the symbol A. So it is half into 3 by 4 into 3 by 4 is 9 by 32. Similarly, P of AC, P of CC is occurring twice there, so it is 2 by 32. Similarly, CB, CA, BC and BB. Now, G2 or the information content per symbol when two symbols are transmitted in a sequence is 1 over n. N is here 2. Now, the summation of all those probabilities, joint probabilities which are listed above, that I have simply put as 2 into 4 into, that is because there are probabilities occurring twice with the same number. See, this 3 by 32 is occurring 4 times. So I have simply put 4 into 2. 9 by 32 is occurring twice for AA as well as for BB. So I have put it as 2 into 9 by 32. And remaining is occurring only once. That is 2 by 32 LG of 32 by 2. That is 2 by 32 is occurring here. That is only CC. But it is occurring in both the tree diagrams. So G2 is computed, G2 is coming as 1.2801 bits per symbol. G1 was 1.5614 bits per symbol, whereas G2 is 1.2801 bits per symbol. What does it mean? It means that G1 is greater than G2. When a single symbol is emitted, the information content is more. When two symbols are emitted, the information content is less. This is what is that theorem's meaning. Ultimately, if n tends to infinity, that Gn tends to h. Gn tends to the source entropy itself. That is when I was telling you the example of English language, Sanskrit language and even Chinese language. And I was telling you that when the number of symbols increases, it doesn't mean that the information content increases. It doesn't mean that way. For example, in English we write water. For the same thing in Kannada we write neeru. For the same thing in Telugu we write needlu. For the same thing in Tamil we write tanni. For the same thing in Malayalam we write vallu. And for the same thing in Sanskrit we write jalam. For the same thing in Hindi we write pani. Now think about all these languages which contain different sets of alphabets. But it doesn't mean that more number of alphabets in a language will lead to more information. It doesn't mean that way. Information content is actually reducing when the number of symbols are increasing. That is what is the theorem here. So why I told you that the proof of this theorem is beyond our curriculum, because the proof is really very lengthy. And we should again appreciate Claude Shannon and his team. Later on, many people worked on this information theory and they have found out all these beautiful findings of their research, that how information and probability are related and how sequence and probability are related and how sequence and entropy are related. And all these findings have helped us in developing better communication systems. As I've been telling you from the beginning, the goal of any communication system is to convey more and transmit less. When we transmit less, we save lot of resources. When we save a lot of resources, we reduce the cost of the transmission. But the information has to be conveyed as it is, without any compromise in the quality of conveying of the information. We can always have a compromise in the transmission cost by transmitting less and by conveying more. And this particular goal is achieved by means of all these findings. That is how information theory is utilized in all the communication methodologies. So, the conclusion is when the number of symbols in a sequence increase, the net information content reduces. Okay. If at all I have to give you one real life example, let us say I send you an SMS which is containing only, let us say, 5 words. And let us say I send the same SMS which is containing the same information, but I may put some 50 words. Unnecessarily, I may put some 50 words. Now, the people who read the SMS with 5 words will be more. The people who read the SMS with the 50 words will be less. Because who will go on reading the big sequence which is containing the same information content? It is possible that the information content can be crisp and small. It is possible that the same information can be lengthy and boring. For example, if a politician is in front of a mic set, I am not telling all the politicians, there are many very good politicians as well. I am referring to a particular politician, let us say, who just wants to pass the time over the stage. Imagine that way. Now, if that particular politician is having a mic set in his hand, he may go on speaking for 1 hour. He may keep on repeating the same thing again and again. But the net information content may be only worthy of 5 minutes. Whatever could be told in 5 minutes, if he keeps on dragging for 1 hour, now who will listen to that 1 hour of speech which is containing repetitive information? Now, that is the finding which is mathematically done here in this information theory, where G2 is lesser than G1, which is mathematically proved. Similarly, G3 will be still lesser than G2, and if the number of symbols increase, if let us say n is infinity, then that G will converge towards H itself. That is the source entropy itself, which simply means that we need not be sending sequences of lengthier nature which will have a lesser information content. That is the idea of this Markov source exercise. Let us compute messages of length 3. P of A, using the same tree diagram, we can find out the probabilities for all these sequences of length 3. AAC, ACC, like that we go on. CCC was occurring in both the tree diagrams as I had mentioned earlier, so it is considered here. Otherwise, no other sequence is occurring twice anywhere. Now, these are all the values for all these sequences till BBB. Now, we can have G3. G3 is 1 over n. N is now 3, and it is the summation of all these. I have put 2 into 6 into 6 into, because there are same values repeated 6 times and twice. So finally, we get G3 is 1.1396 bits per symbol. As I was telling you, it is further reduced. So it can be seen that G1 is greater than G2, G2 is greater than G3, and G3 is greater than H in accordance with the theorem stated. G4 will be still lesser, G5 will be still lesser, that way it goes on. Now you see the value of G3 is 1.1396 bits per symbol, whereas the value of H is 0.8113 bits per symbol. So you can see that if at all G4 is there or G5 is there, its content will reduce. Let us say G infinity is there, G infinity will converge to 0.8113 bits per symbol itself. So that is what is the outcome of this particular theorem. Let me continue. I have put a small note. Summation of capital P of Mi, Lg of 1 over capital P of Mi is given the symbol H of S bar to the power I. This is a typical notation used in the textbooks. Instead of writing this whole thing as a big number, big expression, what they write is they simply write h of s bar to the power of I. So G1 is h of s bar, it is anyhow to the power of 1 because it's a sequence containing single symbol. G2 is h of s bar to the power of 2 divided by 2. Now don't think that this is s bar square. It is not s bar square. It is simply a notation. Now G3 is h of s bar to the power of 3 divided by 3. Why this is divided by 3? That is that 1 over n. Here it is 1 over n divided by 2. It is 2. That is why it is written this way. So sometimes you will see that in the textbooks you will have such notations, that is h of s bar to the power of 2. That simply means that it is sequence length having 2 symbols. Now, whatever I discussed, I have written it in the notes. I'll just read out quickly. It is evident from the previous exercise that when a source is emitting symbols in dependent sequence, the average information content per symbol decreases with increase in the message length. It is a dependent sequence, remember this always. All the symbols are statistically dependent. When the symbols are statistically dependent, more number of symbols doesn't mean that more amount of information is conveyed. So the average information content per symbol decreases with the increase in the message length. This decrease in entropy is highly structured messages requires lesser number of bits per symbol. See, this decrease in entropy in highly structured messages requires lesser number of bits per symbol. In the third module, we have a method of source encoding, where we ourselves are going to encode symbols based on their probabilities. For example, if there is a message called hello, H-E-L-L-O, for this hello, how it will be transmitted in a channel. So we will have to convert it into binary digits or bits. Now when we convert this H-E-L-L-O into bits, H-E-L-L-O, they are statistically dependent symbols in the English language. So when we encode this word into binary sequence, naturally we can have a shorter binary code. Why? Because when the sequence length increases, information content reduces. When the information content reduces, the same information content can be represented by a lesser number of bits. We are going to do that in module 3. Now, whatever is the concept that is being discussed now, this is applicable there in module 3. That is the outcome here. Outcome means the decrease in entropy in highly structured messages requires lesser number of bits per symbol, which means for H and for E, for L, for O, we can have lesser number of bits. And using this lesser number of bits, we can convey more and we can transmit less. That is our essential objective. So this decrease in entropy in highly structured messages requires lesser number of bits per symbol, thus yielding the effective utilization of the resources. Please understand this clearly. I am going to underline this. The decrease in entropy in highly structured messages, what does it mean? Highly structured messages means statistically dependent symbols. That requires lesser number of bits per symbol, thus yielding the effective utilization of the resources. Means with the lesser amount of resource, we can transmit lesser number of bits but we can convey larger amount of information. I just want to give you a live example of how at hotspots Wi-Fi connections are utilized for those wireless devices. For example, let us say at MG Road, there is a hotspot, and at MG Road, so many people keep visiting. Not now. Now the number of people visiting to MG Road is really very less. But whenever the things resume, anyhow the things are going to resume in future. So whenever things resume, again people will be crowded at the Majestic area, people will be crowded at MG Road Brigade Road area, people will be crowded again in Mantri Mall or in Orion Mall. It goes on this way. So now imagine at the junction of Brigade Road and MG Road, there are so many people coming over there with their mobile phones. And imagine there's a hotspot there. Now the hotspot is supposed to provide Wi-Fi service to these people. Now simply imagine hundreds of people coming to the same area, still people will be getting the network there. There are hundreds of people visiting the same area, people will get in the network there. That is happening by means of a method called spread spectrum. You are going to study about it in the next semester in the course called Digital Communication, and in the 7th semester you have one more course called Wireless Communication, where you are going to study in detail about how exactly the spread spectrum technology works. Spectrum is being spread and the information is transmitted with a wider channel using the same wireless channel. That means using the same free space itself, multiple subscribers are given effective network service. Now that is possible because of the findings in this information theory. That way this is related to spread spectrum. The decrease in entropy in highly structured messages requires lesser number of bits. When it can require lesser number of bits, using the same channel, larger number of subscribers can be given effective communication network. That is what it means. Decrease in entropy in highly structured message requires lesser number of bits per symbol, thus yielding the effective utilization of the resources. Just to give you a funny example, imagine that we have these BMTC buses which are always overcrowded. Not now again. Whenever the things resume, again they will remain overcrowded. Even in the past also, they used to remain overcrowded. Where always on the steps people used to keep on hanging, and BMTC driver was forced to always close the doors just to avoid the people falling out of the door. This is the typical situation in Bengaluru city, where the people commuting are more in number, whereas the public transportation is having less in number. The number of BMTC buses plying in let us say in prime time, or to say the morning 8:30, 9 o'clock, or evening 5:30, 6 o'clock, that is when maximum people commute or travel. So at that time, more number of vehicles are required, because that is a busy hour. In the busiest hour, largest number of public transport vehicles are required. But many times it will not match. When it does not match, at that time, buses remain overcrowded. Now I am giving a funny example. Think about the same people, instead of having that height and weight and size, let us say all those people are of half the size. Imagine a person having a 60 kg weight, or a 5.5 feet height, or having, let us say, what is my width? I am just imagining. My width may be around 1.5 feet now. My chest area width may be 1.5 feet now. I am imagining that way. Maybe instead of that, all these people are having half of their dimensions. Half the weight, half the height, or half the width. Now think that way. Double the people can be packed into the same BMTC bus now. Instead of 60 people in the BMTC bus, there can be 120 people in the BMTC bus, because the people size is reduced by half. Of course, the height has no meaning there, even the weight has no meaning there, but the width has the meaning there. But only the width cannot reduce just like that. That is why I gave the example of all the three. Okay. So that way, even though this is a funny example, you can visualize that if the size of the people is reduced by half, then the same resource can carry double the content. Now that is not possible in the case of the BMTC bus or in the case of the people, but that is possible in the case of the information theory. How? Here the decrease in entropy in highly structured messages requires a lesser number of bits per symbol. That is what the meaning of that G1, G2, G3, G4, G5, like that it goes on. Even though the information content does not increase there, the advantage is that we can convey the same information with lesser number of bits. That is the idea here. When we can convey the lesser number of bits, naturally for the same resource, we can send more number of bits which belong to other subscribers also. That way we can effectively utilize the resources. Now, if at all nowadays we are enjoying this digital communication with the much lesser cost, that is because of the advent of the information theory itself. Now, you and me are not really paying much for the present mobile phones communication. Sometimes it is totally very less when compared to our electric bill at home, or when compared to our milk bill at home. The mobile bill per month is actually maybe lesser. Now the JioNet, if you subscribe for a few 84 days, maybe around 500 rupees you are going to pay, and he is going to give you a large bandwidth there. Now you can make calls also, you can have a internet connection also there. Now what is the cost you are paying for that? The cost you are paying is much lesser. Now if you go back about 20 years or 30 years before, what was the cost of making a mobile phone call somewhere in 1970, 1980? After 1980, the GSM standard evolved, and at that time, even the mobile calls were very expensive at that time. When the mobile phones came into the market, even the analog phones, when they came into the market, the cost per call was very expensive at that time. But now think about the situation where the number of subscribers have increased. Number of people who are using the mobile phone is increased. Still, the people paying for those calls or for the service is actually really very less. Why? Because of the advent of a technology called spread spectrum, because of the advent of a technology called TDMA, CDMA, along with FDMA. Frequency division multiplexes, time division multiplexes, code division multiplexes. Gradually, the technology evolved from 1G to 2G, 2G to 2.5G with the GPRS, from 2.5 to the 3G. Now from 3G we are moving on to 4G. Gradually, already we will be moving on from 4G to 5G. And through all these generations of cellular networks, we are able to communicate effectively, and we are able to save the cost of the communication also. All that is because of this one theorem, right? All that is because of this one theorem, that we can pack more amount of information into a smaller packet, and we can transmit more amount of information that way with the same resource. That is where you may think that what is there in this information theory as such, what Claude Shannon would have worked on. Claude Shannon has worked heavily in his complete lifetime on these findings only, because of which now we are enjoying this particular cellular communication or wireless communication. Because of him only, now I am able to take this online class to you, because I am also using these wired and wireless channels for having an effective communication with you. Now, let us see how to construct a statistical model. I am almost coming to the end of this particular topic, but this topic is a slightly lengthy topic. So wherever required, I will have to give you more examples so that the concepts are really very clear. So let us see how to construct a statistical model. Let me take a small break to sip water. The development of a model for an information source involves two steps now. You have seen in the earlier example that there are two states and there are transition probabilities. You have seen that. Now, how that model can be constructed for an information source? That is what is the discussion now. We have an example of the same later on. So now we have to convert or we have to model the information source. There are two steps. One, A is the development of the model structure. B is the estimation of the parameters of the model. Now, the first step is performed by knowing the physical nature of the source. The second step is performed by means of the statistical estimation procedures. We should know the physical nature of the source. Naturally, we can write a model for that. That is this A, development of the model structure. Now, to estimate the parameters, now the second step is performed by means of the statistical estimation of the procedures. The estimates based on the data from large number of sources for a short time are called ensemble estimates. Here we use some typical words. Till now we have been using symbol and sequence. Now we are using a term called ensemble. Now ensemble is nothing but the behavior of this particular source for a short term. So the estimates based on data from large number of sources for a short time are called ensemble estimates. Estimates based on the output of a single source for a long period are called time averaged estimates. Both will be equal if the source is ergodic. Why? Because in the ergodic process, anyhow time is being averaged. So both will be equal. Let us have an example. I may not be able to finish this example today because it's a lengthy example. At least let me start this example. We have an exercise, 15th exercise. Construct a model for the collection of 400 cars whose information is to be transmitted every second. The test data is given as follows. Imagine in a highway there are 400 cars. And imagine the information of these 400 cars has to be transmitted to the nearest traffic police station. Imagine that way. Now there are 400 cars, their information has to be transmitted every second. Actually, in developed countries like USA and Germany, in many such developed countries, this is already existing. There is no traffic policeman to regulate anything there. Everything is automated there. Even in the highways, this information is transmitted to the nearest traffic control centers or traffic police stations, where people's movements are monitored. If at all an accident or a crash happens, before that they should be predicting, and in some way they can take urgent measures so that heavy calamity can be avoided or even the calamity can be reduced. Just to give you an example, in Gulf countries, there are 8-lane highways, 10-lane highways, 12-lane highways. Just like here in India right now we have 6-lane highways. There they have 8-lane, 10-lane, 12-lane highways. And the lane at the middle is having the highest speed. Lane at the periphery is having the least speed. In between there are lanes marked for different speeds. Okay. So let us say in the middle lane, there are cars moving at a speed of, let us say, 160 kilometers per hour, or maybe 200 kilometers per hour, or maybe even 240 kilometers per hour. Whatever is the highest speed on the speedometer or on the gauge there, they may try to achieve that. Because the mid lane is the lane which is having the fastest traffic or fastest vehicles that can move. Only the people who are able to move in that speed, they only get into that middle lane because they want to reach the destination faster. Now imagine that in the middle lane, let us say somebody loses control over his vehicle. What happens is almost everybody in the middle lane are moving in a speed of, let us say, 200 kilometers per hour. You can think about one particular driver losing control in that vehicle. Now naturally, let us say he applies brake for some other reason, and suddenly when he applies brake for some other reason, all the cars which are behind him, they'll be crashing on him or her, and there can be a much bigger calamity. And this is a fact in the Gulf countries. So, in such cases, such things can be avoided by means of what? By means of immediate safety precautions. Actually, nowadays they have enough safety precautions, automated safety precautions, where there are no police constables handling those traffics. It is not possible for the police people to handle such the traffics where the cars are moving in 200 km per hour. So there are automated safety measures. Let me not go in discussing all those things. I gave you that example only to tell you that why this exercise is realistic. So construct a model for the collection of 400 cars whose information is to be transmitted every second. The test data is given as follows. Now let me discuss the test data only in the next class because it's already time now. See you in the next class.